Welcome back to chemical bonding. We're going to continue on with building larger molecular compounds, and we're going to look at some special molecular compounds that involve something called resonance and coordinate covalent bonds. We're also going to do a little bit of review when it comes to naming compounds. In your textbook, this is pages 28 to 35. So by the end of this lecture, you'll be able to draw possible Lewis structures for molecules with more than one center. We've already tried a few. We're going to be able to describe resonance and coordinate bonding. And we're going to be able to draw electron diagrams and structural diagrams for resonance molecules and also for some polyatomic ions. We're also going to review the rules for naming binary and some of the common organic compounds. So for the binary compounds, it's both the molecular and the ionic. So for molecular compounds with multiple centers, in some compounds, atoms bind together more in chains than they do in around just one atom, or especially if you have more than 5 atoms, well then it has to bond in some kind of chain. So we'll look at the molecule here, C2H4, and we've already done one similar to this, but when we look at this molecule, and we follow the same steps, we have 2 carbons plus 4 hydrogens, so we have 2 times 4 valence electrons plus 4 times 1 valence electron, so we have 12 valence electrons. From that, if we take a look at what a carbon atom looks like and what a hydrogen atom looks like, we know that carbon is going to be our center. And since we have 6 molecules, we know that we have to have at least more than one. And since we're binding always the electron deficient molecules to each other. So the 2 carbons are going to be attached to each other, and now we start adding hydrogens. Now, when I put a hydrogen here, I'm going to kind of mirror that and put one here. Since this carbon's been satisfied by one hydrogen, it makes sense to add another hydrogen to this one so that they're equal. And again, another hydrogen here, and another hydrogen here. Fill in your bonding pairs. Bonding electrons. So we have a total of 2, 4, 6, 8, 10 electrons. We need 2 more. There's only 2 spots left, one there and one there. Since our carbons aren't happy, they're going to have to form a double bond. So we're going to share these 2 electrons, and now we can draw a structural formula for it. We got carbons sharing 4 electrons, so they're double bonded, and hydrogens, 2 hydrogens for each with a single bond. And that would be how we do a molecule that has more than one center. Technically, it has 2 centers, one around each carbon. We can even get bigger molecules. Here's a chemical formula for urea. And for bigger molecules, it isn't that much different. We're going to start with our electron count. So we have 2 nitrogens plus 4 hydrogens plus a carbon plus an oxygen. So for our electron count, we're going to have 2 times 5 plus 4 times 1 electron plus 4 electrons plus 6 electrons. And so we're going to have 10, 14, 24 valence electrons. And here's where you're going to really see that structural formulas are much nicer and neater than Lewis, but we always start with the Lewis structure. So there's nitrogen. We have some hydrogens, a carbon, and oxygen. And so when we take a look, carbon is going to be our most electron deficient molecule. And so this carbon is going to go as our starting point. Now, before I go any further, when molecular formulas are drawn out like this, for example, this formula could have been written as something like N2H4CO. Technically, that has the same number of atoms. the reason it's written out this way is it's trying to show you a little bit about structure. So it's trying to say that these things are close together, these things are close together, and these things are close together. So that kind of gives us a clue as to what we're trying to build. So we start with our most electron deficient atom. Our next most electron deficient atom, just to get a place to start with, would be nitrogen. So we're going to bond the nitrogens to the carbons. So there's a nitrogen there and a nitrogen there. Now we've dealt with both our nitrogens, we need to deal with our next most electron deficient, and that would be the oxygen here. It needs 2. Now we have a bunch of places to choose. Because the molecular formula up here put the O beside the C, I'm going to do the same thing. I'm going to put the O beside the C, I'm going to put it above, I could have put it below, same thing. And now I have just my hydrogens. Since carbon has 3 bonds already, I'm going to use the hydrogens and put them around my nitrogens also. Our formula kind of gave us a clue as to where the hydrogens should go. The hydrogens are attached to nitrogen. So I'm going to put a hydrogen here, and a hydrogen here, and a hydrogen here, and a hydrogen here. And now I'm going to make sure I show my bonding electrons for all of those molecular bonds. So there's all my bonding electrons. Now I got to go and fill in all of my other electrons to see if there's any multiple bonds. And so I need 24. I have 6, 7, 8, 9, 10, 11, 12, 13, 14 there. I need to add 10 more. So 1, 2, 3, 4, 5, 6. And now all the orbitals have at least 1 electron. I need to add another 4. And so I'll go through and start putting them in. So there's 1 there to make nitrogen happy. He'll have 8. I'm going to make this nitrogen happy as well. He'll have 8. So I need 2 more. I'll give them both to oxygen, because oxygen is supposed to have 2 lone pairs anyways. And now I take a look, and here I see 1 electron that needs a buddy, and here I see another electron that needs a buddy. So these two can be shared. Carbon and oxygen can share 1 more pair. They're going to end up having a double bond. And now I can make my structural formula. So I have H, N, H, bonded to a carbon, to another nitrogen, a double bond for the O, and note I don't have to draw any of my lone pairs. So the structural formulas are much cleaner in appearance than the Lewis structures. The Lewis structures help you set things up. If you skip the Lewis structure, there's a good chance you're not going to get the structural formula right. So resonance. Some molecules have more than 1 reasonable Lewis structure. If we take a look at sulfur trioxide, sulfur trioxide will look something like this. It has these 2 electrons here that are lonely. They would end up being shared, and there's a sulfur trioxide. I have 1 double bond, but we could have chosen any one of those oxygens to have been deficient. So in our top picture, we chose this oxygen to be short an electron, but we could have just as easily been short on this oxygen or short on this oxygen, which would have changed the placement of our double bond. So with resonance, it turns out that the placement of the double bond in our picture is arbitrary. And remember, we're always trying to represent something in the real world that's moving and has lots of movement, lots of motion, with a static 2-dimensional picture. So these aren't exact pictures. They're the best representation you can do with the amount of time we want to spend on representing it. So the placement of the double bond was arbitrary. It could have been between any of the sulfur and oxygen atoms. So and experimentally, it turns out that all those bonds are the same strength, which what it sort of means is that all those electrons are being shared equally. So the way we represent that is we say, well, this sulfur this sulfur trioxide kind of oscillates between 3 possible forms. One where the double bond is between sulfur and each of the other oxygen atoms. So to represent residence, we put these square brackets on, and we use these arrows in between each of our structural formulas. And so this would be the resonance structure for sulfur trioxide. Coordinate covalent bonds, sometimes only one atom contributes both electrons that are being shared, and we often see this in polyatomic ions. And we create them the same way as we create any of our other molecular formulas. We get our electron total, we build our structure, and here we know nitrogen is the most electron deficient, so it's going to be our center. Notice that because we have a positive charge here, we have to subtract one electron from our total. And so what that means is if we take a look at our electron count, we get 5 electrons from nitrogen, we get 1 electron from each of the hydrogens, but we're going to subtract 1 electron because it's an ion with a +1 charge. And so we do the same thing. We have 8 electrons, we put in our 8 electrons. Now it turns out that nitrogen, when it's all by its lonesome, looks like this. What that means is both of these electrons were donated or used to share with this hydrogen. This hydrogen kind of came on, it was a hydrogen, little positive ion that came in and hopped on to our nitrogen. So that's what a coordinate covalent bond is. Once the structure is made, we have no idea which of these pairs is actually shared. It could have been this pair, the nitrogen donated both, or this, or this, or this. It really doesn't matter which. Since it's an ion, we put our brackets around it, and we make sure we show our charge on the outside of it as well. But otherwise, the steps are the same as when we draw any other structure. Here we'll try one. So, sulfate ion. We'll get our total electron count first. We have a sulfur plus 4 oxygens, plus we have 2 extra electrons because the charge on this molecule is 2 negative, 2 extra electrons. So sulfur provides 6, oxygen provides 6 electrons, plus we have 2, and so we have 24, 30, 32 electrons. So now that we have our electron count, we'll take a look at the atoms that we have. We have a sulfur, and we have an oxygen. Now, they both have the same number of valence electrons, but because we only have 1 sulfur, I'm going to use that as my center first, so our molecule is going to have some symmetry to it. So we have our sulfur. We have 4 oxygens, so it makes sense that we'd have 1 oxygen on each side of the sulfur. And now we fill in our bonding electrons. So there's our bonding electrons, and now we need to have a total of 32. We only have 8. And so now we start filling in our orbitals. Each orbital gets 1 first. So around the molecule we go. That was 12. I needed a total of 24, so I'm going to have 12 more. And what that means is each of our oxygens is going to have a full set. So there we go. Every atom in this molecule has 8 electrons in its valence shell. We have our total electron count, and we have 2 extra electrons, the 2 that we added before. So that would be the Lewis structure for our structural picture. And these are nice because we don't have to write down all of those lone pairs. There would be the structural diagram. Oh, sorry, this question only asks for the Lewis structure. So here's the Lewis structure. This would be the answer that we're looking for, but you could also do a structural diagram as well after, if that's what the question needed.